Hello, Wait, welcome back. You're doing well. Nice job on your midterm, mate. Good morning, Olivia. Welcome back. Nice job on your midterm. Good morning, Abby. Welcome back. Hi, Nalia. Welcome back. Hope you're doing well. Hey, Nathan. Good morning. Welcome back. Good morning, Sabina. Hey, Ty. Welcome back. Good morning, Justin. Hey, Gianella. Tuma, welcome back. We're doing well. So you have to make up the midterm, or Shizo, we have to talk. You took the midterm, but I don't think you submitted it. So, we have to talk about that. See what's going on with that one. I didn't get yours. Hi, Karen. Welcome back. Hi, Alina. Hey, Gianna. Welcome back. Yeah, Shizo. For your midterm, I did not. Did you take it? You submitted it? For some reason, your score is not coming up, or it's saying it's not graded, so I'm not sure on that one. I'll take a look at that again today. I'll have to get back to you on that tomorrow. I'll have to talk to the administrator on that. Thank you. Hey, Destiny, welcome back. Hope you're doing well. Destiny, you have to submit your midterm. If you don't turn your midterm in or don't complete it, then it's going to be a 0. So please make sure you do that. Jennifer, as well, please complete your midterm, submit it. For some reason, I'm not seeing it's completed on your end. So I don't know if you submit it. If you don't turn it in, folks, it will be a 0. Jessel, good morning. Welcome. Hey, Todd, welcome back. Hope you're doing well. Fatuma, welcome back. Good morning. Hey, Fatuma, welcome back. And Emin, welcome back. Hope you're doing well. Hey, Evan, welcome back. Good morning. All right, good morning and welcome back. I hope you guys are all doing well and staying safe. First and foremost, Joey D's not here, but Amaya, Destiny, Jennifer, and Shitso. If you did not complete, this is a general statement to all of you guys right there. If you did not complete the midterm, that has to be completed. That's number one. And if you did complete it, please make sure you submitted it. I'll check again a little bit after class to make sure you guys at least this isn't updated, or if something went wrong, maybe on our end. So hopefully you completed it. If not, you need to turn that in, or it's going to be a 0. So please check that on your end. Hopefully remember how to get to that again for the midterm. So go to, obviously, Buzz, type the password chem is fire, and then you could do the midterm again, or what it may be. Please check the attendance to the left. Please make sure it's accurate and precise. If I made any mistakes, please let me know. Kara, Victoria, I don't think Joe's here. Amar and Maya. If you're here, please let me know. All right, let's wrap up on the midterm. So the midterm, the 45 questions, out of 3 different classes, the average for that midterm was an 81. So average for that midterm was an 81 out of all 3 classes, which is pretty good. You guys in this class did extremely well. Hopefully you did your own work. Hopefully you didn't really cheat on this. Sorry, Mara, I'll edit that. Hopefully you did your own work. The range so far for this class is 60 to 100. So a lot of people did really well. So that means you guys are paying attention to the review. You're paying attention to the process of the notes. You're paying attention for the examples. Obviously, you're paying attention for the exit passes. So you should know how to do that. So good job to those of you who actually did really well. If you didn't do as well as you wanted to, then maybe your notes weren't very good, or maybe you weren't taking your notes. Maybe you're just logged in and you're just going through the routine, saying, oh, I'm here. I'm going to put my music on, zone out for 84 minutes. I'm just going to watch this cartoon. It's only one more episode, one more cartoon. But that's not going to help you out. Whatever you put into something is what you get out of it. If I go through when I go through your guided notes, if you don't complete your guided notes, it's easy for me to grade, number one, but you're not going to get anything out of it. You're probably not going to do too well in the exit passes if you're not doing the notes. I told you that's what guides our class. So it's up to you. If you don't complete the notes, that drives our class, then you're not going to do well at the examples. You're not going to do well on the exit passes nor the benchmarks. So it's on you. At this point, it's on you. There's a lot of really good scores. If you didn't get what you wanted, maybe you have to put some more effort in. All right. There was one poor question on the midterm, which I really don't like, but I'll have to talk to the other chemistry teachers about it as well, see if I could keep it or scratch it. That was on the CH4. It was CH4. I want to know if it was a polar or non-polar bond. We didn't really talk about CH4 a lot yet. We knew that was a symmetrical compound molecule, but the electronegativity difference was a little off in the window that we had, if you remember that question. But I'll talk to the other teachers about it. Maybe we could scratch that one, maybe not. But anyways, any questions on the midterm? Yeah, some of you guys should be proud. Some of you guys did really well. All right, let's see what's going on for the COVID report first. I do want to blow about this one. So the COVID report, I didn't go through it yesterday, the midterm. Check it out. There are 6,872 cases, active cases in Oneida County. There's 7,926 that are resolved. 320 deaths. So I like that first column right there, total active cases. We have more resolved cases than active cases. That's a good sign. We're headed in the right direction. There's 320 deaths, so that's still, think about the impact. If that's your grandmother or aunts or your mother or father, think of all the families that has impacted. I'm sure if that was someone like really close to you, maybe it is someone really close to you that has passed from COVID. I'm sure that's not just a number. It's your loved one that you care about. There's 148 people in the hospital and 26 people in ICU. Vaccination numbers, you could check them out. I'm not going to go through that. But the number of daily positive cases for COVID, I'm liking this. I'm liking the way this curve is forming now. So the second curve, you can see it. It looks like we're on the downward portion of that curve. It's roughly my average. That looks like, as of now, let's hope as of now that's a climax at that date. But now it looks like the average of these values are starting to decrease quickly. That's good. Hopefully it drops off to, I'm guessing, hopefully it drops off to like 50 or under 50, and then maybe at that point we'll be back in the classroom. It's going to take a while before you have zero. A long time before you have zero, but if we get below 50, I could see us in the county. If we get below 50, I could see us getting back to school. I don't know. I don't know about that at all, but again, as a scientist, I could see us going back to school for average around 50. So hopefully we get there so I could actually meet you guys as well. But anyways, last few days data, we had 98 cases on the 25th. The 24th, there's 83, so below 100. And then the 23rd, there's 114 cases of COVID in Oneida County, which is awesome. Why? Because last time we had days below 100, yeah, I wish we could go back to. You guys are missing out on stuff. You're missing out on your friends, your social interaction, chemistry class, live chemistry class in person with chem labs. You're missing out on those stuff. Missing out on athletics. But anyways, last couple days we have below 100. If we scroll on back a couple months to awesome chemistry, it looks like we're in like the periodic table unit maybe, or Thanksgiving time. So like around Thanksgiving, 27th of November, there's 67 cases. That was the last time we were below 100. And we have 2 consecutive days below 100, so that is pretty cool. So these holidays, like, it looks like, if we're predicting, these holidays of Thanksgiving and maybe whatever you celebrate for Christmas, Hanukkah, whatever, those really threw a damper in our curve, I'm guessing. All right, so there's a COVID report for today. Let's check out what's going on in chem class today. It's going to be a light day. Been working pretty hard for a while. I don't give you too much free time. Today might be a day, will be a day where I give you a little bit more free time. All right, so woohoo, here we go. We're halfway through the year. The quote of the week comes from Richard Branson. If your dreams don't scare you, then they're too small. Go out there and make some bigger dreams. So if your dreams are too small and you're not nervous about them, reach a little higher. Daily agenda for Wednesday, January 27th, 2021. Today's a day 3. We are doing a new unit. We're starting a new unit. We're going to get a snapshot of a new unit today. It's on properties of solutions. We'll go through some basic terminology of solutions. If you need to make up the midterm, you probably want to talk to me. Send me a chat privately, and I'll show you how to do the makeup of the midterm. So I already put your name in the chat. Please make sure you have that resolved today or tomorrow. We're going to start off with a YouTube video. Then we'll get to some guided notes. And the second half of class is going to be more of a recap on the first half of the year on the greatest discoveries of chemistry. It's a Bill Nye, the science guy, greatest discoveries of chemistry, but he's serious in this video. A couple of things to analyze. Let's check out the classwork. Where have we been throughout the year? If I go to classwork, you can see the tabs over to the left of what we already accomplished and went over. And then you can see what's left. So here we go. You have Unit 1, Science of Verb. We already did that. Unit 2 is Matter and Energy. We already did that. Unit 3 is the atom. Unit 4, periodic table. Unit 5, spent a ton of time on Unit 5, chemical bondings, ionic bonds, covalent bonds, metallic, and hydrogen bonds. All right, thanks, Jitso. Appreciate it. And now unit 6 that we'll go through is going to be properties of solutions. So that is going to be a quick unit. It's not going to be that long. Unit 7 is called kinetics and equilibrium. Those are rates of reactions. Unit 8 is oxidation and reduction. That's going to take some time. A lot of times students say this is the toughest unit of the year, so brace yourself once we get there. Hopefully it's not. Unit number 9 is acid, bases, and salts. Unit 10 is organic chemistry, which is covalent bonds. And the last one is nuclear chemistry. So you can see what we have left for the year, 6 through 11. Then we're done. Then we can review. Hopefully you have that Regents, because I think you guys will be ready for it. All right, so that's where we're going to be going throughout the duration of the year. Start off with this flick on what solutions are. You already know what solutions are. You go through one thing quick. You already have an idea what some solutions are. If I check out Nalia's flow chart, we went through solutions or mixtures a little bit. So this flow chart we did in Unit 2, we've been talking about this stuff for a long time. So this flow chart we started off with, we started off in Unit 2 talking about matter and energy. We defined these basic things, but that's all we really did. Then we talked about unit number 3 was the atom. We talked about an element and the atom. Unit number 4, so we talked about the atom for a unit number 3. There's unit 3. Unit number 4 was on the periodic table of elements. We had a unit on that. And then unit number 5, we talked about was the chemical bonding. So we should know a little bit about a compound. We should know about covalent bonds, ionic bonds, metallic bonds, hydrogen bonds. And unit number 6, the next unit we're going to be going through, you could guess, it's going to be on mixtures. We're covering all of this stuff again. So mixtures, homogeneous, heterogeneous, aqueous, solutions, all that stuff is going to be highlighted in this. So way back when we did this little flow chart, you probably didn't realize we're going to be taking different portions of the year with these units, but we have been. All right, so solutions. Start off with this flick. It's a crash course. Pull out some information, pull out some key terms from this. This is where we're going to be going for the unit. Here we go.
I want you to think just for a second about breathing. But don't just think about the fact that you are breathing. Think about all the variables that have to be just to create the air and to make the air oxygen in the air. But also, if the air was just oxygen, you would die. The oxygen has to be mixed with nitrogen and other gases, and the whole concoction has to be at the right pressure and temperature in order to deliver the amounts of O2 that you need. The air that you are breathing is a solution. Also, not to belabor the point, but you are kind of a solution as well, albeit a sentient one. A solution, you'll recall from back when we were doing my dirty laundry, is a mixture in which the particles of a solute are dissolved in the particles of the solvent. So what's the solvent in air? Well, whatever there's more of. So nitrogen is the solvent, and oxygen, carbon dioxide, argon, and a bunch of other gases are dissolved in it. All solutions have the qualities that they do because of the same 3 properties: molecular structure, pressure, and temperature. These are the factors that affect a substance's solubility, the amount of solute that will dissolve per volume of solvent. Whether we're talking about the air that we breathe, the water that fish breathe, the bubbles in Coca-Cola, or the toxin in the tissues of the Japanese pufferfish, what usually matters most about a solution is how much solute is in it. Often in the lab, we use placeholders like dilute and concentrated when talking about solutions, but those are vague terms, and we should generally be as precise as possible. Here are a few ways to do that. We can describe a solution by its molarity, the number of moles of solute per liter of solution, its molality, the number of moles of solute per kilogram of solvent, or its mass percent. The mass percent of a solution is the mass of the solute divided by the mass of the solution, all multiplied by 100. So in a can of your average soft drink, there's about 33 grams of sugar and a total mass of 355 grams. Divide the mass of the solute by the mass of the whole thing times 100, and the mass percent of the sugar in solution is 9.2%. Easy peasy there, but the more interesting question here is why? Why can you even dissolve so much sugar in a can of soda, and what about all that carbon dioxide gas? What's happening here? How does the stuff go in the stuff, and where does it go, and what's actually happening at the molecular level? Well, the first thing to keep in mind is that not every solvent can dissolve every solute. Gas molecules don't interact that strongly, so gases pretty much always dissolve in each other. But liquid solvents have a ton of molecular interaction, so the structure of the individual molecules determines whether a substance will dissolve and how well it will dissolve. Polarity is, of course, the biggest bit of this. For a substance to dissolve, it needs to interact favorably with the solvent. This only happens if they have similar polarities, which allows them to form cool in-solution structures spacing the solute particles out evenly. Topic change. Say you're on a first date at a sushi restaurant, and you want to be all cool and nonchalant and I'll tangle with death if death wants me to, so you order the pufferfish, otherwise known as fugu. Fugu contains a poison called tetrodotoxin, and even in the hands of chefs who know what they're doing, it makes your lips go numb just at the taste of it. If the chef makes a mistake and you eat the wrong part of the fish, the tetrodotoxin will mess with your nervous system and cause paralysis, suffocation, maybe some death. Why? Well, in part because of its polarity, and yours. Tetrodotoxin is it dissolves easily in polar solvents, like water. And who's made mostly of water? So if you've watched Crash Course Biology, you know all about sodium channels, the tunnels on the outside of nerve cells that allow them to communicate with each other. Well, tetrodotoxin is really good at binding to those channels, messing up your nervous system. Body is just one big aqueous solution. Tetrodotoxin pretty much has free reign to just jump on every sodium pump you got. Now on to the next attribute that affects solubility. Let's assume that you've survived the first course of your meal and you order a soda pop. To get all those little bubbles that make carbonated beverages so refreshing and tingly, carbon dioxide must be dissolved in the water. But how do you shove a gas into a liquid? A gas gets dissolved into a solution the same way David Bowie and Freddie Mercury collaborate. Under pressure. What? As previously noted, I am old. It's not just the pressure outside of the solvent, it's the partial pressure of the solute. Quick review, partial pressure is the portion of pressure caused by the gas we're interested in this case, carbon dioxide. Gas molecules, as long as they have kinetic energy, are going to want to escape the solution, so they will be creating an upward pressure on the surrounding gas. In order to keep the CO2 dissolved, the partial pressure of carbon dioxide in the gas outside the solution or higher than the pressure of the carbon dioxide molecules pushing their way out of the solution. That's why soda bottles are nice and taut when you squeeze them. That little bit of gas up there is pressurized carbon dioxide. And also why, when you open the can, a huge rush of carbon dioxide molecules bubble out of the soda, because the normal partial pressure of CO2 in the atmosphere isn't enough to keep it from escaping. So, to get the carbon dioxide in there, all you need to do is dramatically increase the pressure of CO2 outside the liquid. And this is what's done in soda manufacturing plants. In fact, if you have a soda stream, you can do it right in your own home. Now, it's easy to calculate this change in pressure thanks to William Henry, a friend of John Dalton of Dalton's law of partial pressures. According to Henry's law, the concentration of a dissolved gas equals the partial pressure of the gas above the solution multiplied by a constant that expresses the solubility of the gas in that solution. And we can use Henry's law to figure out how much carbon dioxide is dissolved in our can of soda. The pressure of CO2 in a can is 5.0 atmospheres, and you can look up the solubility of CO2 in an aqueous solution, 3.4 times 10 to the negative 2 moles per liter atmosphere. So the concentration of dissolved CO2 is 0.17 moles per liter. Now, there are 355 milliliters, or 0.355 liters of cola in a can. How much volume would that CO2 take up at normal atmospheric conditions? Whip out your trusty ideal gas law, and we find at atmospheric pressure and 298 kelvins, or room temperature, 0.060 moles of carbon dioxide will expand to about 1.5 liters. That's A lot of burps, something else to keep in mind on date night. Finally, in addition to polarity and pressure, it's temperature that affects solubility in the most complicated and therefore interesting ways. When we're dealing with solid solutes and liquid solvents, their total solubility generally goes up as temperature increases. This is a fact that you already know if you've ever tried to put a bunch of sugar into your iced coffee. The solubility of gases, on the other hand, is the exact opposite because colder molecules have less kinetic energy and are less likely to escape the surface of the liquid. So the upward pressure they exert is lower than it would be in a hot liquid. That's why it's safer and cleaner to open a can of soda pop when it's cold rather than when it's hot. While this phenomenon might result in a bit of a mess in your house, it's a much bigger deal for fish, who need oxygen dissolved in water to, breathe. At 4 degrees Celsius, the solubility of oxygen in water is about double that of what it is at 25 degrees Celsius. Trout, here in Montana, are highly evolved to that nice oxygen-rich water. But summer heat waves can cause the amount of oxygen in the water to drop dramatically, and cold water fish can get pretty unhappy. Also, fortunately for fugu, it's a tropical fish, so it's perfectly evolved for 25-degree water. And unfortunately for all of us, that brings us to the end of this episode of Crash Course Chemistry. If you've been paying attention today, you learned that solutions can be described in terms of molarity, molality, or mass percent, that polar solvents tend to dissolve polar solutes, and nonpolar solvents tend to dissolve nonpolar solutes. You also learned about Henry's law, which states that the concentration of dissolved gas equals the partial pressure of that gas above the solution multiplied by a constant, and that there are a lot of burps in every single can of Coke. This episode of Crash Course Chemistry was written by Kim Krieger, the script was edited by Blake DiPestino and myself, and our chemistry consultant was Edie Gonzalez. It was filmed, edited, and directed by Nicholas Jenkins. Our script supervisor was Catherine Green, and our sound designer is Michael Aranda, and of course, our graphics team is Thought Cafe.
All right, so there's a little crash course on solutions. Let's see where we left off. Unit number 6. Please open up your guided notes on solutions. So here we go. On the top of the stream, there's a couple things there. I have the textbook. I also have the guided notes there as well. So if you want the textbook, you want to read through the textbook because maybe you're just not understanding it through Mr. Brown. Maybe you just don't like his personality, the notes. I don't care what it is. But there is a textbook there that you could use that I submitted that if you want to read through it, you could read through it, or it could read the text to you as well. So if you want that book in hand, you have the ability to go through this as well. So obviously just open up the text, find out where we're at or what you want to learn about, online student edition, and then you could complete or read whatever you want from the textbook. So you do have a textbook for this class. It's a digital one. You can see what the topics are: properties of solution, concentration, all the information from the text. And again, it will read it to you if you want to. So find a portion which you want to read, whatever.
Agitation. If a teaspoon of granulated sugar, sucrose, is placed in a glass of tea, the crystals dissolve slowly.
All right, so obviously I'll read that to you as well. So I attached that on the classroom page in the event that you want to follow along. Next up, if you go to the guided notes, this is the assignment. Some of you guys just simply are not completing the guided notes. And when you don't do that, I have zero sympathy for you that if you don't complete the notes. So please open up the guided notes. I hope it's not like this. Great. I'm guessing all of yours have this highlighted. Is that true?
No, mine aren't highlighted.
Oh, good. So hopefully you can open it up. Hopefully it's not highlighted. I thought I made a copy of this the right way, but I didn't. Hi, Kara. We're taking some notes right now. Let me fix my attendance quick. All right, so open up your notes, and I'll open up a fresh copy of my notes as well. And we'll start our note packet for today. So again, first half of class is going to be notes. Second half of class, we're just going to watch a video on the greatest discoveries of chemistry. Start fresh, fresh and clean. So fresh start to the quarter. So fresh start to the quarter, a new unit, second half of the year. All right, if you want to title it, feel free to title it, but obviously it's going to be your document. I gave you access to edit this. Change mine to period 3-4. This is my guided notes. Properties of solutions. All right. So here we go. Unit number 6 is going to be properties of solutions. If you want to throw your name up there, feel free to. If you want to throw the date up there, feel free to throw it up there when you started this unit. I like to see it just for reference point, where I was at this time in the year, and you probably don't care about that as much. So again, everything that I put in my notes, I will highlight. I don't know if there's a feature where you could just keep the highlighter on every time you write. I got to look into that. Someone asked me last class on that. There should be a way you could automatically have it highlighted or what. But I know when you start off a document, then you could do it. But I don't know if it's already started on Docs that it will allow you to highlight or change the text automatically to save it. All right, so unit number 6 is properties of solutions. Why are solutions important? Because we use them all the time. We have solutions all around us. They're not just pure substances. They're more like mixtures that we consume or use or have in our lives. This unit will explore many types of solutions. We'll talk about the concepts of properties of solutions, and we'll figure out why these reactions take place in solutions. So a lot of chemical reactions take place in solutions, and we'll discover why in this unit. The natures of the properties are the ways to express concentration of solutions. So if you go in your medical drawer at your house, maybe your cabinet has some medical supplies, maybe it has rubbing alcohol or some nail polish remover. On that, there's going to be percents of solutions. And we'll jump into like details of why they're listed on there. So our goal for today, first half of class, there's some weird guy up there, is to get through topic number 1. So I'll go through it at a nice rate. After that, we'll watch a video on greatest discoveries of chemistry. So this first topic is mainly on solution terminology. Here we go. A solution. I will, again, highlight it, and I'll bold it. A solution is going to be a homogeneous mixture. So we know the difference between a homogeneous and a heterogeneous mixture. A homogeneous mixture is the same throughout. Homo means the same. Geneous is going to be a mixture. So same consistency throughout. Homogeneous mixture, there's not going to be any particles or chunks of a solid particle. A solution is a homogeneous mixture of a substance in the same phase, same physical state, same phase, same physical state or phase. So it could be a solid, it could be a liquid, or a gas for a homogeneous mixture. In a solution is going to contain atoms, or it could contain ions, or it could contain molecules. Atoms, ions, or molecules. Atoms are neutral. Why? Because the protons and the electrons are balanced out. Ions are atoms with a charge, so ions, they either lost or gained electrons. Molecules are going to be like covalent bonds or ionic bonds of one substance spread uniformly the same throughout the second substance. So I like to think of like table salt and water. Take the table salt, mix it with the water. What happens? You have a mixture. You have a homogeneous mixture. You're taking two things, mixing them together to produce a homogeneous mixture. Or if you make Kool-Aid, you take your Kool-Aid. How do you make Kool-Aid? You take a pitcher, You take the powder of Kool-Aid mix, pour it in. Take the sugar, pour it in. And then you take the water, and then you stir it on up. Some of your Kool-Aids might taste a little bit different than your friend's house. We'll talk about that later. When it's solid, when salts, not solid. When salts, NaCl, is stirred into water, what happens here? The ions separate. The individual ions, again, atoms with a charge, of salt separate uniformly. Thanks, Destiny. Just saw that. Separate uniformly and spread throughout the solution. We should know what table salt is. Sodium chloride, NaCl. Let me draw an NaCl over here to the left. An atom of NaCl. So you have an Na, and you have a Cl. NaCl. Nah. So sodium and a chlorine. Anybody remember sodium's charge on the reference table? Oxidation number. What's sodium's charge? It's in group 1. What's sodium's charge? Sodium ion charge. Yeah, sodium's +1. It's in group 1. How about Cl's charge? Anybody remember that one? It's a halogen. Cl's oxidation state. Some of you guys probably memorized it. It is a -1, so a +1 and -1. That's what brings these two things together, positive charge and a negative charge. What happens when NaCl is dumped inside of a lot of water? That's what happens. So if I take NaCl, let me switch this up for a second, and I'm going to take that molecule of NaCl, I'm going to put it inside a big beaker. It's going to get a little messy around here. It'll just be a beaker. Big beaker. Should have put a background behind this, but I didn't. All right, so this is going to be a beaker. Inside that beaker, we're going to have some H2O, water. This blue stuff's my water. So I'm taking the NaCl, I'm dropping it inside of water. So let me draw some water molecules, at least one water molecule. Inside a water molecule, you have H2O. Here's an O, and I'll make an H as well. 2 H's. H. Looks like Mickey. HH. This is my oxygen, and this is going to be my hydrogen. H has a charge, and O has a charge. O's charge, there's only one charge for H on the reference table. O's charge is going to be a -2. If O is -2, H has to be, let's say, attractive. It's got to be a positive. So H is going to be a positive charge. That's what makes the molecule for H2O. The positive charge and the negative charges cancel on out. So positive attracts to the negative. Positive attracts to negative. For NaCl, the positive attracts to negative. So inside of this water, this graduate cylinder or beaker, there's a ton of these H2O molecules. And then I drop some NaCl in there. So what happens when you drop the NaCl in there? It's going to dissolve. Why is it going to dissolve? It's because the Cl, as soon as that NaCl comes in, the Cl is going to attach to, think of the charges again. The Cl is going to be attracted to, that negative charge is attracted to the positive of H. So all these H's are going to attack the Cl to separate it. For the Na, what's going to happen? Na is a positive charge. What's going to happen? The O's, which have a negative, are going to attack this guy and say, come here, I'm going to separate you two. And then what's going to happen is that Cl is going to go off on its own way. It's going to separate this way. The Na is going to separate its own way. It's going to separate the other way. They're separated. It's going to make a homogeneous mixture. So they're going to dissolve. There's a diagram on the next page which you'll see, which is probably better than that. But here we go. Types of solutions. Types of solutions, a couple different types of solutions. The first one, which we will not spend a lot of time in, is going to be a solid solution. A solid may be dissolved in another solid. And when that happens, it's going to make an alloy. So when two solids dissolve into each other, they could. It makes an alloy. How do you do it? If you heat something up, if you heat a metal up to a liquid, take two liquids of metals, mix them together, it'll give you an alloy. Like brass or bronze or stainless steel. Those are all different forms of alloys. When metals are mixed, to form a solution. The result is called an alloy. So alloys, I think of like the rims on cars. Alloys are going to be several metals or a couple metals. That's the best way I could think of memorizing that. An alloy is going to be a mix of two or more metals. The homogeneous of two or more metals. Probably not going to see many examples like this. A couple years ago, I went to Philadelphia, Pennsylvania with a senior class trip when I taught at West Canada. And we had the opportunity to see the Liberty Bell in Philadelphia. There's the Liberty Bell. There's me back in the day and a couple of my old friends. That's Ronald Stewart. So there's Liberty Bell, good old times. And that's an alloy as well. I saw that picture and I figured, hey, might as well throw that cool kit on this slide. The most common type of bonds that we're going to see are most common type of solutions. Most common type of solutions, though, that we're going to analyze in this class is going to be like a liquid. Most common types of solutions in which a liquid or even a solid liquid or solid dissolves in a liquid. So like your table salt and water, mix those two things up. Those are the common examples you'll see here in chem class. So probably not solids, solid and solid, probably gonna be like a solid and a liquid dissolving, or even like a liquid in a liquid. Common type of solution is one in which a liquid or a solid is dissolved into a liquid. So just like your table salt and water, or making Kool-Aid is another example as well. Next portion, some S terms that you should be aware of. A solute. Solute is a substance that is being dissolved. Solute is what you add to the solution. The substance that is being dissolved. If you're taking table salt in water, the thing you add is a solute. It's going to be the table salt. The solute is typically going to be the smaller quantity of the solution. So think about it. If you make salt water, you're adding a little salt, but you have a ton of water. So solute is a substance that is being dissolved. A solvent is a substance that dissolves the solute. So in this situation, the solvent would probably be the water dissolved. Water is the most common solvent. A lot of time chemists use water to dilute chemicals. Or at your house, you look at your health and beauty drawer of your house, your cabinet of your house with your cosmetics in there. There's going to be like a lot of dilution with water. A lot of solutions are made up of, are mixed with water. You go to your nail polish remover or rubbing alcohol, there's a percent of the solution. That percentage is going to be dissolved with water. We'll talk about that later. Water is the most common solvent. Solute is a smaller thing. Solvent, probably water. All right, water solutions are called aqueous. Or aqueous. You'll hear it both ways. Aqueous or aqueous. I don't care how you say it. Tomato, tomato. Water solutions are called aqueous. The notation is going to be a lowercase aq. So anytime you see aq, it's going to mean mixed with water or homogeneous mixture. AQ is used to show that the substance is dissolved in water or mixed with water. Mixed or dissolved in water. We know that though. AQ means homogeneous mixture, dissolved or mixed with water. Okay, once you have that, we're going to scroll on down. We'll analyze the diagram that I was trying to make. So you have the reaction NaCl, sodium chloride yields Na plus Cl. This would be a decomposition reaction. You're breaking down the compound to two smaller things. So thinking about that equation for a second, NaCl, decomposition, what's going to happen? Na is going to break off and Cl is going to break off into two different ions. How does that happen? You're mixing it with AQ. You see the AQ there? It's being mixed with water. So you should be able to read that, understand what kind of reaction it is. You have water, which water in this situation is going to be this molecule, H2O. It's polar. Hopefully you remember it has a delta negative, slightly negative, and a delta positive charge there as well. Delta negative went to the higher electronegativity value. So you have delta negative, delta positive. That's water. But then this big chunk here, that's going to be NaCl. So that big thing right there, it's a crystalline structure. That's NaCl. You should be able to look at this and say, oh, which one's Na, which one's Cl? Checking it out, NaCl, I have a positive charge. You told me earlier the positive charge belongs to the metals, which is Na. But we also have the negative charge, which is going to have to be the Cl. So what's going to happen when Na and Cl separate? When these two guys start to separate, what's going to happen? So this Cl, focus on the Cl. The Cl is a negative. So since that's a negative charge, it's going to want to lock in or separate with a positive charge. Which one's positive out of water, H or the O? The H is delta positive. So the positive and negative are going to attract. You can see the example over here. So there's my Cl isolated in the middle. There's my negative in the middle. And then what's closest to it are my H's, which are all positives. So all these positives are going to say, come on over. Come on over. It's a pretty cool chemistry party over here. I have a lot of positive charges. I want to separate you. So all these little circles I just made are all positives. And they're attracting to the negative chlorine. So that's going to make the the Cl separate away from the Na. What's going to make the Na separate? You can check this out. You can see the positive charge is going to have to attract to a negative charge. So again, my negative charge is right there, which is O. O is -2. You can see the positive charge in the center of the diagram to the top right. That's my Na. And on H2O, the O's are my negative charges. There's an O, that's -2, -2, -2, -2, -2, -2. So again, all those are my -2 values. Those are all -2s, -2. And that's what's going to make those two attract. So negative to positive attraction, that's what's going to make those separate as well. Does anybody have any questions on that diagram? If you understand that, you're in pretty good shape for this lesson at least, and in this unit. So talking about those charges, positive charge, negative charges attracting towards each other. It's a good diagram. Try to think about that. Maybe you want to recreate that. I'll probably find a diagram or a drawing or a video to help us out with that too. Once the salt of NaCl and the water are stirred in the mixture, it becomes a homogeneous. So once it dissolves, it becomes a homogeneous mixture. Homogeneous. The dissolved particles will not settle. So once they dissolve, you're not going to get those particles back out. Once you make your Kool-Aid, if it's stirred, you made a nice mixture of Kool-Aid. If it's homogeneous. Once it's homogeneous, it's not going back to heterogeneous. You can get those particles back out by maybe evaporation, but you're not going to get the particles. You're not going to get the Kool-Aid powder back. You're not going to get the sugar back. Once it's homogeneous, the particles will not settle. Some properties of solutions you should be aware of. Solutions are homogeneous. Homogeneous mixtures. Solutions are clear in appearance or transparent and do not disperse light. So when I worked as a chemist in West Utica at the brewery, we had to test a lot of the products for color or appearance or by alcohol or by bitterness or density. This is just to make sure that what we see looks right. You don't want to buy whatever, Coca-Cola and not be the right color. If it's not the right color, so if you buy Coca-Cola, it's like red, you're like, oh, this doesn't taste like Coca-Cola. So what you see is kind of what you taste sometimes. So you buy Powerade, if you get that blue Powerade, if it's not the right blue, you're like, oh, it tastes funky. So as QC workers, quality control workers, you want to make sure it's the right color. It's the right haze, clearness. So something we did do tests there was the haze of the products. Maybe it was a beer or maybe even the soda we had to test. We had to put a laser, like a machine, we put like a laser through the product and it had to give a certain haze or certain transparency as you put that laser through the product. If it wasn't clear enough, that could tell you that maybe it was something wrong with it. Maybe there's a bacterial infection that maybe took over the product as it got moved. Maybe that told us that they're not cleaning the tanks appropriately. Maybe someone messed up the recipe. So those are different things we detected throughout the plant. If you live in West Utica, hopefully you could scrap up $5 to go check out that tour. It's a pretty interesting place that's in our backyard. At the end of the tour, you'll get some nice root beer at the end too for the $5. But it's a huge place. There's a lot of tanks there. It's an impressive operation. And it's definitely related to properties of solutions right now. Solutions will not settle on standing. Maybe you want to wait till you're a little older. Might be more appropriate. So once you have a solution, it's not going to settle without standing, and solutions will pass through a filter. So all solutions have the ability and will pass through like a coffee filter or filter. Properties of solutions or liquid solutions. They have those characteristics right there. All right, there is no exit pass for topic number 1. So the rest of class today, what we're going to do, I'm going to take some time off and give you guys a little bit of a break since we've been going pretty hard. And we're going to watch a video on the greatest discoveries of chemistry. So from here on out, you have the ability to watch this video on the greatest discoveries of chemistry. So enjoy it. Hopefully you can reflect on the year, where we've been. Maybe there's some concepts that we haven't talked about, but you can see we'll probably go through those as well. Nice review for us. Enjoy.
For us, life unfolds on human scales. Miles, feet, inches. But beneath the surface of things is another realm, 1 billion times smaller than we are. A dimension that holds the secrets to understanding our world. What makes steel strong? Why ice cream is delicious. What makes life possible? Secrets that help us create what we imagine.
The human creativity of chemistry, there's just nothing more beautiful than that.
This is the realm of chemistry, and these are its greatest discoveries. Ancient Greek philosophers believed there were just 4 elements: earth, air, fire, and water, and that air was the underlying element, a single substance responsible for the makeup of everything in the world. Centuries later, Leonardo da Vinci was among the first to suggest that instead of being an element, air might consist of 2 different gases. It remained a mystery until our first great discovery. England, the latter part of the 18th century. Clergyman and sometimes scientist Joseph Priestley conducted a series of experiments searching for new airs, what today we call gases. To find out more about what Priestley was up to, I paid a visit to Arnold Thackeray, president and historian at the Chemical Heritage Foundation in Philadelphia, Pennsylvania.
And Priestley wrote and wrote and wrote on every subject that you've ever thought of. He wrote about history, he wrote about religion, he wrote about politics, he wrote about science endlessly. And Priestley was the man who knew everything. He would tell you the practice of it, the history of it, the theory of it, and he was quite literally the man who knew everything.
But along with everything else, Priestley did this famous experiment, right?
That's exactly correct. And there are 2 things that go into that experiment. The one is mercury, this strange substance that's simultaneously a liquid and metal. And that's just crazy. I mean, who ever heard of a liquid metal? And so it was really puzzling. What is this thing? And people were fascinated by it. And so they wanted to explore it. And of course, the other thing that went into it was the technology to deal with gases. And here in Priestley's experiments and observations on different kinds of air, we have the technology of collecting gases over liquids.
In tubes that you could see through.
Exactly. So you can see the gas, you can see what's happening to the gas, and now you really are in business. What Priestley does is he takes a burning glass to give him heat, a lens. He focuses it on this orange powder, the mercuric calx. He heats it, it changes into this metal mercury, and a gas comes off. But Priestley doesn't really realize what it is that he's found.
The answer would emerge in 1774, after Priestley paid a visit to Paris and shared the story of his discovery with another scientist, Antoine Lavoisier.
Paris is a marvelous place for Priestley to visit because Antoine Lavoisier is in Paris, talk of the town, doing the work that will end up as his elementary text on chemistry. And Lavoisier, who is also mucking about with gases, hears what Priestley's done, is fascinated by the report of this new air, decides he'll repeat the experiment. He has lots of apparatus, better apparatus. He's a meticulous experimenter, and among other things, he weighs things. Lavoisier, by weighing, says something is being emitted. He calls the thing emitted oxygen. He rewrites the whole script of chemistry, and he creates a list of elements that we still use today: oxygen, hydrogen, sulfur. You can correctly say that Priestley discovered oxygen, but Lavoisier invented it. So with Priestley's experimental work on gases, with the discovery of oxygen, with Lavoisier's articulation of a system of language, we have the whole conceptual scheme in which 19th century academic work is built, 20th century industrial innovation. We have pharmaceuticals, we have biotechnology, we have cell phones, we have plastics, that's exactly right. And all these things begin with the discovery of oxygen. That's where it starts.
That's a lot to breathe in. In the early 19th century, a British schoolteacher named John Dalton was hard at work, pursuing his fascination with chemistry, which would lead to our next great discovery. Dalton's experiments showed that the known elements such as oxygen, hydrogen, and carbon combined in definite and constant proportions. From his calculations, he hypothesized that the elements must be made up of smaller, invisible pieces of matter with relative and distinctive weights. He called these pieces of matter atoms. So, what did Dalton discover?
Dalton's great discovery was what he called the relative weights of ultimate particles.
Ultimate particles.
That's what he called it. It's a lovely phrase. Later on, when he went public, it becomes atomic weights, and we know it as atomic weights, but it was ultimate particles.
So he used the word atoms.
He used the word atoms. The idea of an atom, of course, goes back to Democritus. The problem is, it's an idea, is it any use? And Dalton was the man who made the idea useful. That was his great contribution.
From his work, Dalton developed what came to be known as his atomic theory, a revolutionary new system that defined the relationship between atoms and the elements.
And it's an enormously simple system, and Dalton thinks very simply, very visually. Here are the elements, here are the weight of the elements, here are the complex molecules, and it's a wonderfully effective system. It connects the thing that chemists can do, weigh things in balances, with the things that you can't see, the ultimate world of atoms. That's genius.
How important was Dalton's discovery? His atomic theory helped generations of scientists further unravel the mysteries of the atomic and molecular world, including our next great discovery. In the early 1800s, French chemist Joseph Gay-Lussac was conducting a series of experiments designed to study Dalton's atomic theory when he observed something odd. When he combined equal volumes of different gases and measured their reactions, the gases often produced twice the volume than he expected. How was this possible? The answer was provided in 1811 by Amedeo Avogadro, a physics professor at the University of Turin in Italy. While studying the results of Gay-Lussac's research, Avogadro had an insight. At the time, it was believed that gases were made of single atoms. Avogadro realized this assumption was wrong. The gases were made of multiple atoms, what came to be known as molecules. The realization that atoms could be rearranged to form molecules was the breakthrough that enabled scientists to move out of the chemistry dark ages and begin systematically creating new compounds. Our next great discovery occurred in the 19th century, when many chemists believed that organic substances from organisms or living things were somehow different from inorganic substances, from non-living things. But that was about to change. In 1828, Friedrich Wöhler was working in his lab when something caught his eye. Wöhler had placed two inorganic chemicals in a beaker, potassium cyanate and ammonium sulfate. Now when he looked at the beaker, it contained a gram's worth of small, white, needle-shaped crystals. What made this remarkable was that Wöhler thought he'd seen these exact same crystals once before, but with an important difference. Those crystals had been organic. He had crystallized them while studying the chemistry of various substances found in urine. To make sure he wasn't mistaken, Wöhler analyzed the new crystals. There was no mistake. These crystals were the same as those he had isolated before.
He had made urea, which was something that had come out of a living thing. He had made it out of inorganic substances. Later he said, in a personal letter, not in the paper he wrote about it, that I have made urea without a kidney. And he knew what he had done.
Meet Roald Hoffmann, winner of the 1981 Nobel Prize in Chemistry for developing a theory to explain organic chemical reactions. So why is this discovery of artificially making urea, why is that a great discovery?
You know, there comes a time when you need a discovery, and it's sometimes a single one, to cross a border, to break down a wall. This is what this discovery was. Wow. It's not that it was so important in and of itself, but at the time that it came, the simple making of urea out of two inorganic chemicals, when it came, it caught people's attention. The whole story of the discovery is about the underlying basis, the building blocks of all matter, organic and inorganic, being the same, atoms.
If these Lego bricks had existed in the early part of the 19th century, chemists could have used them to help illustrate something they were seeing in their experiments. A phenomenon that led to our next great discovery. The atoms of particular elements, such as sodium and chlorine, seem to combine with each other according to fixed ratios. It was this combining power of atoms that inspired German chemist August Kekulé to develop a system for visualizing the chemical structure of various molecules. Kekulé represented the atoms by their symbols, then added marks to indicate how they bonded with each other, like links in a chain. It was a simple yet elegant formula. Chemists now had a device for clearly illustrating the chemical structures of the molecules they were studying. There was just one problem. Benzene was the only known chemical that would not fit Kekulé's formula. Benzene's chain of carbon and hydrogen atoms required more combining power than the formula would allow.
And all these organic chemistry professors are puzzling about it and offering different explanations. And one of them, Auguste Kekulé, sitting by the fire one evening, falls asleep and starts to dream about a snake. And if you think about a snake, what Kekulé dreams of is the snake catches its own tail. And if you think about this, maybe the thing is a ring. And that gives you an answer to the puzzle.
The 6 carbon atoms of the benzene molecule weren't linked in a chain. Like the snake, they formed a ring, each with a hydrogen atom attached, with alternating single and double bonds. Within a short time, Kekulé's insight was confirmed, and its effect was revolutionary. Chemists knew that all organic substances contained 1 or more carbon atoms in their molecules. With Kekulé's discovery, they now had the underlying formula to explain how carbon combined with other molecules to form a world of chemical compounds. The modern era of organic chemistry was born.
Now, with this thing being so simple, that is to say, the snake bites its tail, why is this considered a great discovery?
Here's a recipe for new drugs, new medicines, new understanding. If you go back in time, in Dalton's day, a couple of hundred compounds. Soon it's a couple of thousand. Soon it's 10,000. Astonishing. Soon it's 100,000. Last year, 15 million new compounds were registered, all built on this simple template. This is a work of genius.
In 1869, a Russian chemistry professor named Dmitry Mendeleev was writing a textbook for his students when he began to wonder how he could best explain to them the 63 elements that were known at the time. To help formulate his thoughts, he constructed a card for each element. On each card, he wrote the name of the element, its atomic weight, its typical properties, and its similarities to other elements. He then laid the cards out like a game of solitaire and began arranging them over and over, searching for patterns. Then came the moment of discovery. Before him was something extraordinary. The elements fell into 7 vertical groupings. Each periodic grouping had members that resembled one another, both chemically and physically. Mendeleev had discovered the periodic table of the elements, a map showing how all the elements related to one another. A map so precise that Mendeleev believed he could also use it to predict the existence and properties of 3 elements no one had yet discovered. One would be like boron, he said, one like aluminum, and one like silicon. Eventually, the elements were discovered, and Mendeleev was proven right.
There was actually a little bit of controversy because a German chemist named Lothar Meyer had come up with roughly the same idea. But Meyer didn't quite have as much courage. So that's actually an interesting thing. Here is this German who comes up with the same idea of periodicity, of which there were hints already before, but he doesn't make the predictions that Mendeleev does. So here we see the power of a risky prediction in having people accept a theory. There is nothing more powerful than making a prediction that's not obvious.
And then have it come true.
And have it come true.
Yeah.
The periodic table is our icon. I mean, it's what we associate with chemistry. You go into any chemistry room, you see it.
Why is the periodic table of elements significant? It forever changed the way that everyone would learn and understand the elements. The periodic table of elements is to chemistry as notes of music are to a Beethoven sonata.
In honor of Mendeleev, his name is now literally attached to the periodic table. The element 101 was named after him. It's called Mendelevium.
It's not only chemists who like the periodic table. I hear you carry one around.
I do carry one, yes, sir.
Show me.
You never know. And I seem to use it a lot.
Let's see.
It's a small one.
So I'm going to give you a test. What is under nitrogen in the periodic table?
Nitrogen is 7.
Yes.
I have to think a second.
Under
sulfur.
nitrogen? No, you're wrong.
Oh, God. That's
Close.
why I carry
You're
the thing.
one off. It's phosphorus.
Oh, phosphorus.
Phosphorus
15.
is right.
Phosphorus is 15?
Yeah, you have to add 8 at that point.
See, that's why I carry it. I can't remember. So it's 7 plus 8, 15 phosphorus. Okay. There's a pattern there. I get it now. At the turn of the 19th century, electricity was all the rage. People were busy making batteries and connecting them to just about anything to see the reaction. Electricity was like a new kind of fire. One of the great battery junkies of the day was Humphrey Davy, a self-taught English chemist. In 1807, Davy was performing a battery experiment in his lab. He melted some potash, a mineral found in the ground that also forms in the ashes of wood. Chemists had speculated that potash was a compound of several elements, but had not been able to prove it. Davy wanted to see if electricity might provide the answer. He ran some wires from one of his biggest batteries to the melted potash. Pure potassium began to emerge. Davy had discovered the power of electricity to react with chemicals and transform them. Eventually, electrochemistry led to the rise of the aluminum industry, the production of semiconductors, solar panels, LED displays, even rechargeable lithium batteries. In the 1850s, Robert Bunsen and his research collaborator Gustav Kirchhoff conducted a series of experiments to determine why substances emitted specific colors when placed in a flame. The color they determined indicates what elements are present in the substance. For example, if sodium is placed in a flame, they observe shades of yellow. Copper, shades of green. Strontium, shades of red. That was a good one. While watching the experiments, Kirchhoff was reminded of how a prism spreads light into a rainbow of colors. So, using a prism and the pieces of a small telescope, Bunsen and Kirchhoff built the first spectroscope, an analytical device they hoped would help them see the spectra coming from heated substances. And it worked. As an element was put into the flame of a Bunsen burner, the light from the heated substance passed through the prism of the spectroscope, where it then spread into a ribbon-like spectrum of colors, riddled with dark lines. The combinations of bright colors and dark lines were like barcodes, indicating what atoms were present. When burned, each element produced a completely unique spectrum. Using their spectroscope, Bunsen and Kirchhoff were able to discover two new elements, cesium and rubidium. One day, Bunsen and Kirchhoff decided to test their invention with sunlight. It produced a spectrum that featured two lines that were identical to those in the spectrum produced by sodium. Bunsen and Kirchhoff had discovered the presence of sodium in the sun, 93 million miles away. Suddenly, scientists had a tool to help them study the chemistry of the heavens.
Liftoff. We have liftoff.
Today, the legacy of this great discovery lives on in the exploration of space. A form of spectroscopy is being used to study the atmospheres of planets, to search for signs of water, signs of life. Our next great discovery is the story of Joseph Thomson and the electron.
Here we are.
So everything that we can see is made of chemicals.
That's right.
What's the
And
future?
they're all bonded through electron interactions.
Thank goodness.
The future.
To find out about it, I paid a visit to Harvard University. Dudley Hirschbach is a professor here and winner of the 1986 Nobel Prize in Chemistry for his research into the dynamics of chemical elementary processes.
So Thomson didn't discover the electron.
Well, it's of course said that way, but he didn't discover in the sense that he said, Eureka, I've got this thing, here it is. He did an experiment that allowed him to measure the ratio of the charge, the electric charge, to the mass. And then later he was able to get a rough measurement of the charge and therefore show that the mass was very, very small. It was about 1/2000th of the mass of the lightest known atom, hydrogen atom. So it showed that he could extract in the experiment a very small piece of an atom. Well, that was a tremendous shock. People didn't imagine. Yes, yes, electrical piece of an atom. It was a very small part of the atom.
At the time of his discovery, Thomson was a professor at England's University of Cambridge. He was using a device called a Crookes tube in his experiments.
I happen to have here a little apparatus that's akin to the one that J.J. Thomson used in 1897. It's called a cathode ray tube, just an evacuated little glass cylinder with some electrodes. And we can hook this up and show the key points of his experiment.
A replica of the first CRT.
Yeah, it's the first cathode ray tube. It's ancestor of the television tube, as a matter of fact. You do the last one, and we should get a stream of cathode rays or electrons going there, and it'll show up. A few of them bang into this phosphor-coated piece of cardboard there. Here, I'll give you a magnetic field you can use to deflect the electrons.
When Thomson exposed the stream of cathode rays to a magnet, the stream would bend. Since magnets can only affect matter, this meant the stream of rays was composed of some kind of electrically charged substance called radiant matter. After many hours of observing and measuring, Thomson realized he'd found the first subatomic particles. The ray was a stream of electrons. It was a revolutionary discovery.
Some years later, a student of Thomson, Ernest Rutherford, was able to show that the positive charge in atoms, which of course had to be there to balance the negative charges of these little electrons that were scooting around, was localized in a tiny, tiny nucleus, 100,000 times smaller than the size of the atom. And so almost all the mass was, of course, in that nucleus as well, because electrons are so light.
And that's still the model we have today, right?
That's the basic model for atoms, and of course the key to understanding everything involving atoms.
Like chemistry.
Like chemistry in particular. That's right.
Okay, guys, I'm going to stop it there today. Hopefully you guys got something more, a different insight or a view on some sort of topic of the atom or the periodic table or the history of the atom as well. So that's it for today. No homework yet. Have a good day, and we'll see you guys later. Stay safe. See you guys.
Have a good one, Mr. Brown.
Bye, you too. Take care. See you later. Bye, guys. If you have to make up the midterm, please make sure you have to do it. Do it by today. See you later, guys.